Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be taking a look at episode 13 of our Discovering STM32 series. So, following on from the last episode where we had a look at the Quad Spy peripheral and using the flash memory on the discovery board, in this episode we're going to be looking at the SDMMC peripheral and being able to access SD cards so that we can read data from them and write data to them. In this episode, it'll be similar to what we've done in the last one, a couple of the others, where we're going to go through and have a look at getting a driver written for the peripheral and then putting it through a bit of a testing to make sure that the driver is actually working. In the case of the SD card, it's a little bit different to what we did with the flash memory, simply because the SD card is removable. So we do have to factor that in and do it in such a way that that's not going to cause any issues for any of our other code that may be making use of that driver, so that it can check whether or not there's a card there that is currently mounted properly that we can then read or write to, or whether there's no card available, or whether there may be an error condition or something like that. So to give you a bit of a demonstration of what we'll be looking at, we've got our F769i discovery board set up there, and this is basically a version of the code that we're going to be looking at today. And in this case, it's basically at the moment giving us a bunch of information about the SD card that's currently in there. So you can't quite see it at the moment, but at the back of the board there is an SD card socket. If we eject the SD card, we can see that it automatically detects that there's no card present at the moment, and we can see the card that we're using for demonstration purposes here. It's just your typical micro SD 32GB one, in this case from Kingston. If we pop the card back in, making sure I put it in the correct way around, trying not to block the camera, pop that one in. It's detected an error. Let's try that again. There we go. Mounted at that time, so it's telling us there's a card there, that it's mounted, how big the card is, what size the blocks are on the card, how many blocks there is, as well as a few details about the card itself, what its type is, what its version is, and what class, speed class the card is. So that's a bit of an example of what we're going to be doing. Let's jump over to this one and get some code written. So this is the code as it was at the end of episode 12, just following on from there. And much like with our previous episodes, the code from this episode will be up on GitHub at the end of this episode as well. So I've got, where are we? Where we were actually testing the flash memory driver last episode. So let's remove that bit of code. So we'll still keep it so that it's actually initializing the peripheral there. One of the other things we might actually do as well, because we're getting a fair bit of driver initialization stuff that is ending up in here, we might actually go through and move some of that out and just tidy up our main function at the moment. So let's create a couple of methods in here. Might even just make sure there's a bit more separation between that and some of our other stuff there. Keep that indented like that for the moment. And let's go QA results. I'll call that QA driver init. Don't need to pass it anything. And we'll create one called QA system init. So that we can separate things out a little bit there. Let's grab hold of that stuff. And we're going to pop this down below our main function. Should rename these as functions, considering they're not members of a class. Fix that up here as well. That's a bit better. All right. Now we're going to grab all of our current initialization stuff, cut that and paste it into drivers, and then we do have some system initialization stuff in here, like the LCD, which we're going to move out into here. Okay, pretty happy with that. Which removes a big chunk of stuff in here in our main, in between our system initialization stuff where we're doing our actual boot code from boot.cpp through to our processing loop. So in here we'll go initialize drivers and initialize systems. And let's make sure we get the right names for those. So given that it's returning a QA return value, if it's non-zero then it's an error. So that way we can easily check whether we have an issue or not. And because we've got serial printing out messages and stuff like that in the actual driver init function, we're not going to do anything other than pop it into an infinite loop if it fails. So we'll already be getting feedback out of the serial from that. However, if we get to this point, we know that that's all initialized fine, so we'll pop a message out there. And we might just pop a blank line in after that as well. And in this case, if it's failed, we'll pop out a message letting it know that. Otherwise, if it succeeded, all right. we're just going to make sure that that works before we start adding a bunch more code to it, just to check for any potential issues. Spotted those couple of warnings there. It's because we haven't put our return values in. Now, rather than going to infinite loops in our actual code in here, which we've done for a lot of these drivers, we will instead get it to return, because it's going to go into an infinite loop in our main function if these have failed anyway. So that should be the last one. Yep. All right. Just build that again. Wonderful. Pop that onto our device and we'll just test that, and then we'll get... Really? Device is definitely connected. It just wants to make things interesting today, of course. That's better. All right. So we can see our device is running fine. It's got the just basic stuff that we've got it being rendered to the LCD in the LCD boot up code. As we can see down here, all this rendering stuff here, just to test that that's actually working. Go through and update that at some stage, but we won't worry about that today. So now that we've tidied all of that stuff up, let's get a driver written for our SD card. So we'll create a couple of files for this one. And as I mentioned, the particular peripheral that we're going to be using for this is the SDMMC peripheral. So we'll name the files accordingly. Might help if I named this one correctly. There's that there. Make sure we stick to our naming convention we've been using so far. That's a bit better. Excellent. Let's grab, just grab the header from this one and copy that over to our new header. Mix up our details for this one. It's the 10th of February today. Excellent. All right, fix this guy out. That's all correct. We need our other prevent recursive inclusion at the end of the file. Cool. All right, and let's just copy this over to get our source file ready to go as well. Need to include QAD SDMMC that one. File definitely exists. I'm not sure. Ah, semicolon. No, not semicolon. Not sure why it's complaining. Let's just check that. Aha, one too many M's. Might help if I could read properly right now. Alright, so we're going to set up the driver as a singleton class, much as we've done for a bunch of the other drivers in this series, simply because we've only got the one SD card socket. So therefore we only want one copy of the driver to exist at any point in time, and that's what the singleton class is perfect for. I'm going to create a couple of enums first up though. The first one being this card presence enum, which just allows us to store whether or not there is a card actually being detected as in the socket, which will just have two states, which is card not present and card present. We're also going to create another enum which is tracking the state of the actual driver, which we're going to call card state, and this one will let us know whether the card's not loaded or whether there's an error, or if everything is good to go for us to be able to read and write data. So mounted in this case means that the driver has basically got the card mounted and ready to read and write from it. So that's those guys. Now we'll get to the actual driver class itself. And because it's going to be a singleton, now I'm going to have a private followed by a public followed by another private section. Now, which way do I want to do this? Okay, so first things first, we're going to create a private enum inside the driver just to let us know when we go to actually deinitialize things if we need to do a partial deinitialization due to a failure during initialization, or if everything's up and running and working correctly and we need to make sure that all of the bits and pieces are deinitialized properly. Now that will actually be an implementation method, so we'll pop that in there. If you're a little bit uncertain about classes and singleton classes still at this stage, then there will be some videos coming up on our Unearthing C++ series, looking at those in future. I'm also looking at getting one done probably the next video I do for that series, looking at enums, if you'd like a bit more information about those as well. So possibly going to get that one done after I've finished doing this video. So let's get some private constructor done. So because we're using a singleton class, as we've done previously, our constructor will actually be private because it will be called from inside the class itself. And of course we're going to need to delete our copy constructor and assignment operator so that we can't go and make multiple copies of the class, given that we only have one peripheral that we're going to be using with this driver. So that's our copy constructor and our assignment operator. And I also want a get method to be able to retrieve an instance of the singleton class so that we can actually get access to the stuff inside it. Like so. Alright. Now there's a few other private bits of information that we're going to need the driver to keep track of. We'll store our timeout value in here as well. Could do this as a define outside the driver, but we might just do it this way. Make that 100 milliseconds. Need to track what the state is of the driver. So we need to know whether or not the driver is actually initialized. So we use a QA init state enum for that, which is defined in our setup.hpp file, and we'll use our card state enum that we defined just before in there. Now we'll also want to keep track of the information of the card that is currently inserted as well. So we want to know how big it is. We're going to use a uint64t for that, simply because it's going to be the size in bytes, which can easily get into a value that's going to be larger than what we can fit into 32 bits. Also store the size in megabytes as well. Now, I want to know how many blocks the card has, as well as what the size is of those blocks as well. And we'll also keep track of the other card details as we saw on the LCD before, so the card type, the version, and its class. And lastly, we're also going to want a peripheral handle, so we can use the HAL methods to access the SDMMC peripheral. Which we would call MS handle. So let's do our initializer list in here. So when the class is created, we are not initialized. Our card state, we'll just set to no card at this point. Oops, that's state no card. Set our other values all to zeros. Like so. All right. So we're going to need a few different methods in here, including some initialization methods. These will be static methods so that we can access them for the singleton class, and then they'll be pointing to implementation methods, which are accessed via the get method, as we've done fairly similarly. Dnit. Now we're going to add a processing method here. This will be the method that we call at a regular interval, which checks to see if there is a card present when there wasn't previously, or if we've removed a card, so that it knows whether or not it actually needs to go through the process of mounting the card or unmounting the card. And again, that'll be a static method pointing at a implementation method, and all of the implementation methods, as we've done previously, are going to go into our private section down the bottom. So going to pop these guys in. So these are just going to be pulling information out depending on the actual state of the card at the current point. This get card present method will be calling an implementation method, simply because it's actually going to be checking the pin, the GPIO pin, that tells us whether or not there's a card in the socket or not. And then just the ones to retrieve our card state, size, all of those details, and they'll just access those directly from the member variables in the class. And then finally, we're going to have the methods that allow us to read blocks from the card, to write blocks to the card, or to erase the card. And with these ones, with accessing the SD card, it's all done on a block basis, I guess. So say our block size is 512 bytes, for example, then if we're going to read data from it or write data to it, we're going to do that in chunks of whatever the block size is, so 512 bytes in that example. When we're erasing, we're basically giving it a start and end address of the blocks that we want to erase. So again, it's a block-based system. You can't just go, I want you to do it from byte 4 through to byte 32, for example. You're going to have to erase a particular block, much as you have to read or write a particular block or a sequential group of particular blocks. So that's how that's going to work for us. Then we're going to go through and create our actual implementation methods. And to save you watching me type all of this, we're just going to copy that in. So these are just the private implementation versions of these methods up here. So whereas all of these are static, so that we can access them from outside the singleton class, these are the methods inside the class that can then get access to all of our private data and things that are in the class. So all of these details here. So our static methods can't access this stuff without using the get method, as we've seen here. So when we're returning the card state using this static method, we use get to retrieve the instance of the class, and then it can access that member variable. As far as our private constructor, if you've not seen some of the videos before where we've looked at using singleton classes, this guy is private so that we can't call the constructor from outside of the class, but the very first time this get method gets called, it will automatically call that constructor for us. So say if the first thing we do is call this initialization method after creating, or when we go to set the class up, the first thing it's going to do is call the get method, which is then going to call the constructor, and then once all of that's done, it's then going to go through and call the implementation init function in order to initialize the class. Again, I will be doing a video on singleton classes specifically in our Unearthing C++ series, because it can get a little bit confusing if you're not familiar with it. But in certain situations where, say, we're writing a driver for a system where there's only one copy of that peripheral in the hardware, like we have here, where there's only one SD card socket, then the singleton class is great because we don't need to create multiple copies of the driver. In fact, it's best if we don't, because they could potentially conflict because they'll be trying to access the same hardware. Could end up with a situation where one driver thinks that the driver's not initialized and the other one does, and end up with weird stuff happening. So as far as our actual source file, I'm going to start with our initialization methods, and these are all connected to our implementation methods in this private section down here in our header. So the first two will be to initialize or deinitialize the driver. These ones are fairly simple as far as just going through and checking if we are already initialized and returning OK if we are, because we don't need to then go through the process. Calling the periph init method, which we'll have a look at in a moment. Setting the driver state, so if this is successful to in initializing the peripheral, then we can say that we're initialized. But at this point, we're still letting it think that there's no card, even if there is, and that'll become clear why when we look at some of the other methods. Then we've got our deinitialization method, which basically will go through, make sure everything's completely deinitialized, our peripheral, our GPIOs, all of that sort of stuff, and then set our driver states respectively, so that if we want to completely shut down the driver, we can do that and everything's back to the way it was prior to us initializing the driver in the first place. We're then going to have a look at our peripheral initialization method, which is this guy here. Good to see that it's messed up my indents as it usually does. So this one will get called from our overall initialization method in here. And this is where we're actually going through and getting our GPIO set up, as well as enabling the clock for the SDMMC peripheral. So the particular pins that we've got that we're going to be using with the peripheral will be a clock pin, a command pin, and 4 data pins. So we can see these guys here are connected directly to the actual SDMMC peripheral, and then we have an additional pin which is just going to be used as a normal GPIO in input mode, which is used to detect whether or not there's actually a card in the socket, so that we can then figure out whether we need to go through and actually get things mounted or not. And then we've got our associated peripheral deinitialization methods here, which basically goes through and does the reverse of that. This one's also going to check whether we need to unmount the card. So if the card has been put in there and we've gone through the process of initializing the peripheral and getting to a point where we can access data on the card, then prior to doing all of this stuff, we need to make sure that we're actually unmounting that. So disabling the clock and deinitializing the peripheral, the GPIOs. And we'll notice the deinit mode enum here. And this is so that if we have a failure that doesn't require a full initialization, then we can basically skip doing this step, which we're not going to be using at this point in the driver, but it will potentially become useful for us in future. So let's pop the next one in, which will be our processing method. So this one will get called at a regular interval. I typically find somewhere around 500 milliseconds to 1 second. Could be shorter, could be longer. Probably wouldn't go shorter than 500 milliseconds. And basically what this method will do is go through and actually check whether there is a card currently in the socket, and then if there is, it'll check whether or not we're not currently, the card's not mounted, and then it'll go through and mount it if it needs to. Same as if we're in a situation where there is a card that is mounted or currently in an error condition, and then it detects that the card's removed from the socket, then it will go through and unmount it. And that, as you saw at the start of the video when we got the peripheral error, when it wasn't happy with the way I inserted the card, just taking the card out and putting that back in basically resets things because of this behavior. So it's basically just checking if it needs to mount it or unmount it, and then doing the associated task based on what the previous state of the driver was and whether or not it's currently detecting a card in the socket. So I've got a couple of methods here that we will pop in next. First one is basically checking our card presence pin and seeing if there is actually a card in the socket. So rather than having to call this whole thing each time, basically just gives us one method that returns our card presence enum, just to simplify things a little bit. And that also means that we can have our get card present static method as well as the fact that this gets used by our processing method as well in here. So because it's being used in a couple of different places, break it out into a separate function or method to enable us to do that. And then we've got one that enables us to retrieve the card information from a card. So just using the HAL SD get card info function there. And then if that's failed, just setting all of the associated card details to 0. But otherwise, it'll go through, grab hold of the block count and the block size, figure out what the overall size of the card is by multiplying those together, calculate what the size is in megabytes by dividing that by 1,048,576, and that'll give us the size in actual megabytes, not hard drive manufacturer megabytes. I know they both have two different names. I can never remember which is which. It's mebibytes and megabytes. One one is basically divided by 1,000,000, the other one's divided by the actual number that it should be. Then we have our block count and block size getting stored, as well as the type, version, and class of the card, which are retrieved in our HAL SD card info type def structure that we pass into our HAL method there. So that's those ones. Then we have our method to actually mount the card, which is kind of, I call it mounting. It's kind of initializing the actual peripheral, but I kind of think of it like mounting a drive. In this case, we're basically just going through and initializing the SDMMC peripheral. In this case, it's SDMMC2 that we're using. There is 2 SDMMC peripherals on this board, but only one of them is wired up to be connected to like an SD or MMC card. Telling it that we want it to function on rising clock edge as far as transferring data, disabling power saving, setting our bus width initially to 1 bit, so it's only using one of our 4 data lanes. So we've got the 4 data pins. At this point, when it initializes, it's only using one of those. And then disabling hardware flow control, because we don't really need that. And then just setting our clock divider. And going through and initializing that. If that fails, then we store that we've had a peripheral error. So when we're getting the peripheral error, when we saw at the start of the video, it was either this or the next method that was failing. And possibly because the card wasn't seated in the socket correctly, which is most likely why it may do that. Assuming that that all succeeds, then we can go through and actually tell it that we want it to change from a 4-bit wide data bus, a 1-bit wide data bus to 4 bits, which is what this is doing here. Just the config wide bus operation method, and just telling it to use 4 bits. And then we'll check the card info, so it'll pull a block count, block size, all of that sort of stuff that we saw in this method. And that's pretty much that done. At that point, assuming all of that stuff succeeds, then we're good to be able to read or write data to or from the card, or erase parts of the card if we need to do that. Also have an associated method to unmount the card, which is this one, which basically goes through, sets all of the card information to 0, sets our card state to say that there's no card, and then just deinitializes the peripheral using the HAL method there. So that one's pretty simple. And then we've just got our methods to be able to read data, write data, or erase data from the card, which are these guys here. Let's fix up our indents again. And these ones are just making use of the HAL SD read blocks, HAL SD write blocks, and HAL SD erase methods. The one thing that these methods do as well is first check that the card is actually successfully mounted before trying to do anything with it, so that we're not going to go and even attempt to read or write or do anything with the card if it's not in a state where we should be doing that. So these guys are all fairly simple as well, just a couple of bits in each of them. It's quite a simple driver. The only main kind of difference or slight complication is the fact that we're using the processing method to check whether or not we've inserted or removed a card, and then either initializing the peripheral and mounting things, or deinitializing and unmounting respectively. So a decent bit simpler than what we looked at in the last episode with the flash driver. The one thing we'll also need to do is we can see I've got a bunch of defines to the actual GPIO pins and ports and the alternate functions for the pins that require it as well. We're going to need to pop those into our setup file here. So I like to keep all of the pin definitions for most of the things together, with the exception of the SDRAM, simply because there's a ton of pins. I find it easier just to keep those in their actual driver file, but we can see we've got all of the pin definitions for our user LEDs, our user button, the definitions for our UART1, which is the serial over ST-Link, for our pins to control the backlight and reset for our LCD screen, and then also for our quad spire peripheral and our flash chip. So we're going to add some of those for our SDMMC peripheral. Need more coffee. Like so. And you will find these guys are all in the reference documentation for this discovery board as well. So just our card detect pin, which again just operates as a standard input GPIO, and then the 6 pins that are actually connected to the SDMMC2 peripheral itself. So that's pretty much all we should need to do there. At this point, assuming we've done everything correctly, this should compile, and then we'll jump into our main CPP and pop some code in there to make sure that the card is actually mounting and unmounting and everything correctly. What have we messed up here? Wait, pretty sure that shouldn't be a reference there, maybe. Again, need more coffee. Can never have too much. Yeah, that's better. We still have another error though over in here. So I changed the names of those in the enum I created. So they're a bit different than what they were in my test code. There we go, all built. So what we're going to do is we're going to add a couple of things to our processing loop, along with first up getting that driver initialized and ready to go. So let's add that down here in our driver initialization that we created earlier. And while I think of it, we also need to include our new driver file, which would definitely help. And we don't need to create a class pointer for that because it's a singleton class. So we can just go if QAD SDMMC, and we use the 2 colons rather than a dot or the pointer there to get access to that due to it being a singleton class. So we can see we've done the same thing here with our touch controller and our quad spy driver due to the fact that they're singleton classes as well. So we don't need to use a new operator or anything to create a copy of the class, which is also one of the benefits to using a singleton class. So we're just going to call the init method there. If it returns a non-zero value, then we know that there's an error, because QA underscore OK in the enum is a 0 value, anything else is an error. If that fails, we'll print out a message over serial. We could just print out via serial whether the card is mounted correctly and all of that sort of stuff as well, but we have the LCD screen there and we haven't used it a lot since we've written all of the stuff for it. So as we saw at the start of the video with it showing us the info on the screen, we may as well make use of it. So that's all we need to do to initialize that one. If it fails, we'll print out a message saying it failed, turn on our red LED to let us know something's wrong, and return QA fail. And if it's succeeded, then we'll pop out a message to let us know about that as well, just so that we know what it's doing either way. Go back up near the top of our main file. I'm going to create I don't know if that's actually being used. What have we got going on in our processing loop at the moment? Just our heartbeat LED. So this touch update tick threshold doesn't need to be here. But we're going to create a couple of these. One for our processing method to actually check whether or not it needs to mount or unmount the card. So we'll call that SD card tick threshold, and we're going to do that every 500 milliseconds. And one for actually rendering data to our screen, which we're going to do a decent bit quicker. We're going to do it so that we're actually updating the screen about 30 frames a second, which means that each iteration is about 33 milliseconds. So 33, or 1000 divided by 33 is going to give us about 30 frames a second. So that's those ones. Let's jump back down to our processing loop. We're going to need to create some variables to track the times for both of those tasks. Set those to 0 initially. And we'll create bits that we need for those tasks in our actual processing loop. So add the amount of ticks that has passed since the previous loop to our SD card ticks variable. Check if it has exceeded our threshold. If it has, then we need to go through and do the processing we need to do for that. And reset our tick count for that. Oops. Like that. Do the same thing for our LCD. Like so. Now in here we just need to call our driver's process method like so, which takes care of all of that. If we've inserted a card, it'll mount it. If we've removed one, it'll unmount it or clear any errors. And then for our LCD, we are going to go through and print a bunch of information about the card. Like so. So basically, just create a string to be able to format some data into and print that out. We're going to clear our buffer, in this case our background layer. So layer 1's our foreground layer, layer 0 is our background layer. If you've seen the episodes where we're getting the LCD screen up and running, that'll be fairly familiar. Telling it that we want to draw something in black, then actually going through and drawing a rectangle, set our font that we want to use, and just printing out some text in white in this case. So setting it color to white and just printing out the title, which will be shown at the top of the LCD. And then just sending out data, letting us know if there's a card currently in the socket, what the driver state is currently, so whether there's no card, whether there's a peripheral or a card error, or if it's mounted and everything's good to go, then it's also going to spit out our card size, block count, card type, card version, and card class from our driver. And then finally, just clearing our foreground layer here just to completely transparent, so setting our alpha, red, green, and blue values all to 0, and then flipping both our background and foreground layers so that that newly rendered frame then gets displayed on the LCD. So again, all stuff that we would have gone over previously in the LCD videos, but this is kind of a good example of how we might make use of that stuff to actually start rendering bits of information to the screen. So let's see if that compiles. That should all be all we need to pop in there. 2 errors, what have we got? Same thing. Used a different enum name in here. All compiled. Just going to remove the card from our socket for the moment. Let's copy the code over onto our device. And we can see it's going through and letting us know there's not currently a card in the socket, and the driver is also saying that it's in a state where there's no card. If we pop the card in, you see the card then shows as being present. The driver's gone through and mounted that and gathered the details about the card, at which point we're good to be able to go through and read data or write data or erase stuff on the card. And if we remove it again, you can see it's generally pretty quick with actually going through and getting things happening. The peripheral errors that we saw at the start of the video are basically just from me trying to avoid getting my arm in front of the camera. As a result, the card wasn't quite seated in the socket correctly, so it was enough to trip the card detect pin, but when the peripheral tried to communicate with the card, it wasn't getting good communication. But you can see here that it works fairly well each time. And we can see the card present state actually updates before the rest of it, simply because that's getting updated at the speed that we're updating the LCD screen. So that's actually being updated at 30 frames a second, whereas the drive is only checking whether a card's been removed or inserted every half a second. So that's why we get a little bit of a speed difference in between our card present and our card state. and that tends to be pretty reliable. This is a variation of code that I've used previously on a couple of projects, although I've not done it as not used it in C++ previously, so it's kind of a new thing. And actually it tends to work quite well with integrating it into FATFS. So we can actually go through when we start integrating FATFS as well and make it so that FATFS will actually, if we insert a card, the driver will set up the peripheral and everything like that. Once that's good to go, we can actually immediately mount that drive in FATFS so that we can then access files on it. And if we remove the card, then it will unmount FATFS and then unmount the driver so that everything happens in sequence and get nice smooth operation out of that without any issues as well. So that tends to work quite well. It's possible that the next video that we look at in this series will actually be looking at getting FATFS started. We might do that over the course of a couple of videos rather than just one, because it may tend to be a little bit long, or we may just do it in one video. I'm not 100% sure yet. I do tend to make things up a little bit as I go along with this channel, so that's part of just the way I write code, I guess. So that's what we've got for today's episode. If you've enjoyed this, found it helpful, would love it if you put a like on the video, subscribe if you haven't already. Huge thank you to all of the people that have been watching the videos. The highest, most viewed video on the channel is actually the first episode of this series, which is kind of cool. Considering that that's what I started with, I don't know, 4.5 months ago now. It's been a fun ride so far, and I'm really enjoying making the videos. So thank you to all of the wonderful comments, all of the people that have liked and subscribed, even those of you that have just watched the videos. I think it's amazing that there has been so many views of the videos since I started. If you've got any questions or comments, feel free to leave them in the comments below. We do also have our subreddit and the Gmail address there if you want to leave comments or feedback, things like that there as well. The code from this episode, much like the previous episodes, will be going up onto our GitHub. We'll drop a link to that in the description as well. And a massive thank you to our 3 patrons of the channel. You guys are awesome. Thank you so much for helping to support the channel so that I can continue making great content, or decent content, and keep putting out stuff. So my goal is to get all of the drivers and everything out of the way for this board so that we can actually then start doing some videos on using it in actual projects. But it's good to have a full driver base ready to go so that if we want to throw it at a particular project, then we've got everything we need to be able to get started so that it's nice and easy. Same as with some of the drivers we've been doing in the STM32 basic series. A lot of those will eventually get ported over to this board as well, so that we've got access to all of those drivers on this board. Out of all of the STM32 boards that I use out of my collection, this is probably the one that I've used for most projects. I've gone through a fair few of these ones because they get put into projects and then I have to get more. Yeah, so definitely my favorite board, which is why I do enjoy doing this series quite a bit. So again, thank you to everyone. Look forward to sharing with you what we do in the next episodes, and thank you very much for watching.